Hi, my name is Amir Gilad. I'm from Duke University, and I'll present my talk, Informed Data Science. So data science is at the center of some of the most important decision-making processes, from deciding on the coverage of medical benefits to filtering job applications. While data science can often boost performance, both in terms of accuracy and speed, its complexity and obscurity have led to some gaps in understanding that resulted in several high-profile failures and dilemmas. For example, the Amazon recruiting tool that was gender biased, preferring male applicants over female ones, after it was trained over 10 years worth of biased data. Another example is the alleged racial bias in the United Health algorithm, where the algorithm called Impact Pro was supposed to give a risk score for each patient and ended up preferring white patients over sicker Black patients. For a local example, farmers were fined by the Israeli tax authority, and when they asked for an explanation for the reason for the fine, the only explanation that they got was, this is what the computer output. So to try to understand all of these errors and try to fix them, we can consider just the machine learning model or the algorithm. But that would be looking at only part of the picture, because in practice, in most cases, the data science process is composed of several automatic systems that manipulate and prepare the data in different ways. For example, as we see on the slide, the initial data can be obtained from an existing data set or synthetically generated by an automatic system. Then the data scientist can explore the data and see if it meets the requirements for the task at hand. After that, and based on the results, the data may need to be repaired, then labeled, and finally inputted to a machine learning model, which is trained and evaluated. Now, today, many data scientists perform this process without being able to understand its intermediate results. And errors can occur in any of these systems. For example, the initial data can be limited, erroneous, or biased. Another example is when the data exploration step accidentally ignores crucial parts of the data that make it unsuitable for the task. And another example is where the data repair process that is supposed to improve the quality of the data accidentally introduces errors into it. Therefore, it's crucial to provide users with tools that allow them to do this process more efficiently and in an informed manner that allows them to understand the intermediate results of these systems. We also want to provide guarantees on the results of these tools. So in my previous research, I've developed solutions for the data generation component, the data exploration component, and the data repair component. In particular, I've developed a system that assists in data generation, systems that assist in query formulation, systems that explain the query results, and explore the privacy implications of releasing such explanations on revealing the query. And I've also developed systems that explain the data repair process. And I also have ongoing work on some of the other components. So in this talk, I want to focus on 3 projects. The first one is for generating natural language explanations for query results formulated over natural language interfaces. The second one is for explaining the queries themselves using abstract database instances. The third one is for generating links between synthetically generated database tables. And I'll conclude with some ongoing work and the future directions. So let me start with the first project. And this project aims at providing natural language explanations for query results formulated over natural language interfaces in the data exploration component. This project has been developed and published in several conferences and journals, and it was awarded the VLDB Best Paper Award and the Sigmoid Research Highlight Award. So it's well known that users without technical training have a difficult time formulating database queries. But let me tell you that even expert users can find it hard to formulate queries when they're very complex or when the database is unknown and they don't know the exact structure or the values. This is exactly where natural language interfaces come in. They allow users to formulate their queries in English and then get the results. So let's consider this use case where a user formulates a query over an academic database. So the queries return the organization of authors who published papers in database conferences after 2005. When this query is inputted to a natural language interface, it's automatically translated into this formal query written here in Datalog, and we don't need to go into the specifics of Datalog, but then the formal query is evaluated and the results are returned to the interface to show to the user. Now, one of the results just happens to be Duke University, and then a user who views this result may wonder, why is it part of the result set, or why does it satisfy the conditions specified in the question? So what we'd like to show the user is a clear and concise natural language explanation for this result, such as this one. Duke is the organization of 63 authors who published 170 papers in 31 conferences between 2006 to 2015. So the tool that we're going to use to provide these explanations is called data provenance. Data provenance describes the origins of the data and the computation process leading to the generation of the result. Now, data provenance has several other uses, such as debugging database processes, checking hypothetical scenarios, and verifying the trustworthiness of results. Because of all these uses and the fact that it's been explored by multiple previous work, it's considered the gold standard for these uses and specifically for database explanations. So let's see an example of provenance. Here at the top, we have the natural language query. Below, we have the formal query in Datalog. And here's a model for the provenance for Duke University. This is a provenance polynomial where each monomial represents an assignment to the formal query that resulted in Duke University. Each monomial is composed of pairs, a product of pairs, where the first element of the pair is a variable name from the query, and the second element is the value from the database to which it was mapped. So if we consider, for example, the first monomial, if we replace the variables in the query with the values to which they were mapped to, we get a partial assignment to this query that if we complete it, we would get the result Duke University. So now we asked ourselves the question, how do we translate this model of provenance into a natural language explanation? And when we wanted to solve this problem, we tackled two main challenges. The first one is that the formal model of provenance, as we've just seen, is very far from a natural language explanation. And second, the provenance of even a single result can be very long and convoluted. And we use the structure of the input question to tackle both challenges. For the first challenge, we use the structure of the input question as the basis for the structure of the explanation. For the second challenge, we shorten the provenance by factorizing it using algebraic factorization and use the structure of the input question as a criterion for generating only factorizations that are suitable for natural language explanation generation. So let's go over our framework. Initially, the user inputs a natural language query to a natural language interface. In this case, we've used Amir, which is based on the 2014 VLDB paper. Amir then parses the input question, creating a dependency tree. And then during the process of translation to a formal query, maps the words in the question to variables in the formal query. Our augmented version stores both the dependency tree and the mappings from words to variables. Then the formal query is evaluated using a database engine that stores the provenance. In this case, we've used CELPI, which is based on our 2018 VLDB journal paper. Then the provenance is factorized and an explanation is generated based on the factorization, or it is further summarized and an explanation is generated. Yeah.
Does the dependency tree give you an arithmetic circuit based on the?
It gives me a structure of the natural language query. So I'll demonstrate it in, I think, the next slide. the tree itself.
You cannot get the circuit computing the.
Oh, the circuit itself. So the dependency tree just describes the semantic structure of the sentence of the natural language query. The factorization can be modeled as a circuit. So we're going to link the structure of both of them to make sure that we generate good explanation. Yeah, but that will come next in the presentation. Okay, so let's demonstrate the process of explanation generation first for a single assignment. So here's the dependency tree for the natural language query. As you can see, there's a node for each word in the natural language query. And below some of the words, there's semantic information about their role in the sentence. So now let's consider the mappings that we get from Nalir and the assignment itself. For example, the word organization was mapped to the variable oname in the formal query, and then it was mapped to the value Duke University by the assignment. So once we have the dependency tree and the mappings, we want to convert them into an explanation tree in order to create an explanation sentence. And we do that based on the semantic information given to us by the dependency tree, namely the part of speech and relationship. Based on this information, we augment the dependency tree of the natural language query to convert it into an explanation tree by either adding the mapped value as a new node in the tree or replacing the word with the value mapped to it. For example, the value Duke University is added as the child of the word organization to which it was mapped to. However, the value Junyan replaces the word authors to which it was mapped. So now that we have the explanation tree, we want to create an explanation sentence. We do that by reversing the mappings from words to values and considering the location of the words in the original natural language query. Based on these, we generate the explanation. Duke is the organization of Junyan, who published iCheck in Sigmod in 2014. So now let's consider the general case where a single result can stem from multiple assignments. So meaning we have several monomials in our provenance polynomial. One possibility is to use the previous slide and to generate an individual sentence for every assignment. However, this would result in a very long explanation that would be tedious for the user to read. So instead, we use the already known concept of provenance or algebraic factorization to shorten the provenance and create a single explanation sentence that captures all of the assignments. So now let's consider this provenance polynomial that we've seen before, but this time containing only the values. Here are two different factorizations of this expression. The left one is the shortest possible factorization, and the right one is a longer factorization. Now, the standard in previous work has been looking for the shortest factorization since it's the best solution in terms of storing the provenance. But recall that we are interested in factorizations that will allow us to generate a natural language explanation from them. So intuitively, what we want is a factorization that follows the structure of the natural language query, so we can generate an explanation sentence based on the structure of the natural language query and the factorization. So let me demonstrate what I mean by that. Here at the top, again, we have the natural language query. Here's the shortest factorization. And here's a reasonable explanation sentence based on the structure of this factorization. Now, first notice that this is not a clear sentence. And what's more, the parts in red are not part of the original natural language query, and it's not clear how to automatically generate them. So let's see what happened. Here on the right, we have the dependency tree of the query, and on the left, we have the shortest factorization. Notice that in the dependency tree, the word authors is an ancestor of the word conferences. However, in the factorization, or in the factorization circuit, the value Junyan mapped to the word authors appears lower in the hierarchy than the value Sigmod mapped to the word conferences. So the hierarchies are reversed and the structure of the factorization is disconnected from the structure of the query. If instead we consider the longer factorization that we've seen, which preserves these hierarchies between the words in the dependency tree, we see that we can generate a clear explanation sentence based on its structure and the structure of the natural language Chord. And in general, a factorization that preserves these hierarchies of the words in the dependency tree is called T-compatible, since it is compatible with the dependency tree. So here's our algorithm for generating factorization. And we start by traversing the dependency tree in a top-down fashion, taking out the values mapped to the words according to the order of traversal. If there are several mapped words at the same level, we prioritize between them based on the frequency of the values to which they were mapped. So the guarantee of this algorithm is that we will generate a T-compatible factorization on the basis of which we can generate a clear explanation sentence. So an explanation that is based on a factorization can still be too long at times. So we can shorten it even more by considering provenance summarization. We build on the factorization that we generated in the previous step and choose the level at which we want to summarize. If we choose a specific level, we summarize all levels below. So that means that if we choose a higher level, we would get a shorter explanation that is less informative, like the brackets A. If instead we choose a lower level to summarize, we would generate a longer explanation that is more detailed, like the brackets B, that the explanation based on their summarization contain the author names, for example. Now, ultimately, the choice of summarization level depends on the user's preference. So to assess the quality of our, yes.
לפני הסמריזיישן, אתה בעצם, העץ מכיל בעצם את כל התשובות, את כל הרשומות שענו לשאילתה, ולכן, כמו אתה מניח שהכל נכנס בזיכרון ואפשר לטפל בהכל במכה אחת.
נכון.
שהשאילתה מספיק, התשובה מספיק קצרה כדי שאפשר לטפל בו בדרך הזאת, ואחר כך אתה עושה סמריזיישן.
כן, אם אני עושה תשובה לפי פקטוריזיישן, אז היא יכולה עדיין להיות קצת ארוכה ומפורטת מדי.
כן, לא, אני מתכוון, אבל אם התשובה היא באמת ארוכה, אתה תעבור עדיין קסר, או אתה לא יכול בכלל לייצג אותה בצורה כזאת שתאפשר אלגוריתם סביר לבחור את העץ ולעשות סמריזיישן.
כן, נכון, כן, אבל לא נתקענו במקרים כאלה בפועל, אבל טכנית יכול להיות שיהיו כל כך הרבה השמות.
אם אני שואל, שומעים אותי? מהשמיים. שומעים אותי? כן. אוקיי. רציתי לשאול, מה אם היום יש הרבה מערכות שמתרגמות לשפות שאילתה שלא עברו דרך dependency tree, זאת אומרת, זה הנחה די חזקה להניח שהמערכת שמתרגמת משפה טבעית לשפה פורמלית עוברת דרך dependency tree, זה גם מאוד מגביל, כאילו, את סוג השאלות שאתה יכול לשאול, אז כאילו לאור ההתרחשויות לאחרונה, כאילו איך אפשר לשנות את זה ככה שזה לא יהיה, שלא יהיה את ההנחה הזאת?
כן, אז זו שאלה מצוינת. יש היום הרבה מערכות שעושות natural language, שהן natural language interfaces שבכלל עוברות דרך מודל machine learning. למערכות האלה אנחנו לא יכולים, הפתרון שלנו בעצם לא מתאים, כי אנחנו לא יכולים להסתמך על ה-dependency tree. מה שכן חיפשנו, וזה היה state of the art כשעשינו את זה, אבל מה שכן חיפשנו זה את הגרנטי הזה, שאנחנו נוכל לעשות explanation שהוא מובן. אם אין לנו את ה-dependency tree, אז אנחנו צריכים אולי לייצר אותו באופן מלאכותי. זאת אומרת, נניח שהמערכת עוברת דרך מודל machine learning, אנחנו עדיין יכולים לעשות נתיב עוקף מערכת ופשוט לקחת את ה-dependency, את ה-natural language query, להשתמש בפרסר פומבי ולעשות לה את ה-dependency tree בעצמנו.
מה לגבי האפשרות, כן יש דברים במערכת שמייצרת את השאילתה, כאילו attention וכאלה, שבזמן שאתה מייצר את ה-output, זה מסתכל על ה-input, אם חשבתם על אולי, לא יודע, להסתכל על ה-attention, או איזשהם ייצוגים שה-machine learning model מייצר לאורך הדרך כתחליף ל-dependency tree, שאולי כן יכולים להגיד משהו לגבי איך הקלט מתמפה לפלט, או משהו באזור הזה?
כן, אז את זה לא לקחנו בחשבון, לקחת ייצוגי ביניים כאלה של ה-Machine Learning Model, אבל יש דרכים אחרות גם להסביר שאפשר כן להשתמש בדברים האלה, או אפילו אפשר לחפש הסברים אחרים שהם לא חייבים להיות Natural Language, כדי לנסות להסביר שאילתות שנוצרות ככה. אבל בלי Dependency Tree בכלל, הפתרון שלנו לא כל כך יעבוד. אז אנחנו תמיד יכולים איכשהו לייצר Dependency Tree בצורה מלאכותית.
תודה.
אוקיי. Okay, so to assess the quality of our system, we've experimented with various queries of different complexity, and we've also asked users to formulate their own queries and view the results that they got. So here are some of the use cases and the explanations. For example, for the query, return the authors who published papers in VLDB before 2016 and after 2007. We got the result, for the result Junyoung, we got the explanation that Junyoung published 9 papers in VLDB in 2008 till 2015. Okay, so now we know how to generate natural language explanations for query results over natural language interfaces that use dependency trees. So now I want to focus on a system that explains the queries themselves or complex queries themselves using abstract database instances. And this work was recently accepted to Sigma. So I want to focus on a specific use case first and then generalize the problem. So consider this question given to students in database course as homework to translate to SQL. Find the bars that serve the most expensive beer, liked by any drinker whose first name is E. So here's a student's translation. And as you might have guessed by the red X, this is a wrong translation. And specifically, there are 2 errors. The first one is that the query will consider all drinkers whose name starts with Eve. So the first name can be Evan, for example, and it doesn't have to be Eve. The second problem is that the query will return all the bars that serve the beer not at the lowest price instead of the single bar that serves it at the highest price. And we don't need to go into the SQL syntax for that. Don't worry about understanding the syntax itself. So here's the correct translation, but let me talk about the general problem here, where we want to help the student find the errors in the query and make them understand in the first place that the query is wrong. So on the one hand, we can't show the correct solution to the student because that would solve the homework. But on the other hand, we can't point to the red parts also, hoping that the student would fix them and get to the correct query, because the queries can be very different from one another. For example, the correct query here uses negation, which is not used by the first query. So our solution is to generate abstract database instances that differentiate between the queries. So here's an example of an abstract database instance, or a C instance, as we call it, generated by our solution. So this is just a set of database tables, as you can see, that contain variables and don't cares denoted here by a star. Below the database tables, there's a condition in some of the variables. Now, when the 2 queries that we've just seen are evaluated over this instance, their results differ. The correct query's output is going to be B1X1, since the bar X1 serves the beer B1 at the highest price. However, the wrong query's output is going to be B1X1 and B1X2, since the bar X2 serves the beer B1 not at the lowest price. So generating such abstract database instances has 2 main advantages. The first one is that we can give these instances to the users to analyze and try to understand why their query is wrong and how to fix it. The second advantage is that these instances, being abstract, are closer in representation to the formal queries that we've seen in the previous slide, so they don't confuse the students with with specific values that may lead them in the wrong direction. So now I want to convert the use case that we've just seen to a more general problem of query characterization. So let's consider the difference query, which is just the wrong query minus the correct query. Notice that any database instance that has a non-empty result for the difference query is guaranteed to have a different result for the correct query and the wrong query. So what we want to do is generate database instances that satisfy the difference query. So I'll give a quick overview of our model for queries. We model the queries in a first-order logic language called domain relational calculus, which just means we have a first-order logic formula for a query. And we further model this formula as a tree called a syntax tree. The inner nodes of the syntax tree are quantifiers and connectives in the formula, and the leaves are the basic building blocks of the query called the query atoms. So now we want to understand how to characterize queries using instances. So intuitively, what we want is to know what parts of the query does an instance captures. And for this, we use the notion of coverage, which we borrow from the field of software validation. In software validation, a test suite is said to cover a specific function if this function is invoked by the test.
But the problem is undecidable. Yes, given a query, two queries, and you ask them whether they're different, it is undecidable.
If they're different, yes.
So this is what you ask. So
yeah, our problem will also be undecidable, but it's going to be defined a bit differently. Yeah.
Sorry?
Our problem is, yeah, it's also going to be undecidable, but it's going to be defined a bit differently because I want to generate a set of C instances and not decide if they're wrong, not decide if one query is different from the other. Yeah, but this is very, very close to what I'm getting.
And listen, what is your problem? Given two queries, you want to find the...
No, my problem is I haven't defined it yet, but my general problem intuitively is to characterize a query using instances. Yeah, so I'll define it. Okay, so now the question is, how do we translate this notion of coverage to queries in C instances? So the idea is to use the syntax trees that we've seen in the previous slide. So let me start with a database instance that contains values, which we all know. And here's the syntax tree of the query that we've seen. Now, first, this syntax tree already contains some of the values from the instance, just to show you that this instance satisfies the query. And to define what it means for an instance to cover a specific atom or a specific leaf in the tree, we just say that this atom is covered by the instance if there's an assignment to the variables in the tree such that this atom is fully instantiated, satisfied. So in our case, this ground instance satisfies or covers all of the green atoms in the tree. So now we can notice that the C instance that we've seen at the beginning can be mapped to the ground instance from the previous slide by just replacing variables and don't cares with constants. So to define the coverage of a C instance, what we can do is just intersect the coverages of all the ground instances to which it can be mapped to. And in our example, the C instance that we've initially seen covers the green atoms in the syntax tree. So here's the problem of characterizing a query. Given a domain relational calculus query, what we want to do is find a set of C instances such that each one has a different coverage. And for every satisfying ground instance for the query, we have a C instance in our solution set that has the same coverage. So your intuition was correct. This problem is undecidable. And this can be shown using a reduction from the finite satisfiability problem for first order logic. So what we do, this has been, sorry for the second node, but what we do is we generate an exhaustive set of C instances up to a predetermined size to make sure that the algorithm halts. So the algorithm starts by mapping the free variables of the query to variables in the C instance, creating new rows in the database tables. And then it starts traversing the syntax tree of the query in a top-down fashion, handling each node accordingly and expanding the mapping of each variable in every possible way. So it can consider several C instances all at once, as we can see in the third level of the tree. So the guarantee of this algorithm is that we would generate a set of C instances, each one satisfying the query and each one having a different coverage. Okay, so now we wanted to test the question that we've initially asked and wanted to know how do these C instances do in helping students detect errors in their queries. And to do that, we've conducted a comprehensive user study. The study included 64 students. And we've showed the students a query that contains 2 errors, and we've asked them to detect as many errors as they could. We split the students into 2 groups. The first group was shown 1 ground instance, which is a solution proposed by previous work. The second group was shown at first 1 C instance and then a second C instance with a different coverage. So we can see by the graphs that first, the group that saw 1 C instance, 1 ground instance, excuse me, was not as successful in detecting the errors in the query in general. And for the second group, once they saw the second C instance, they were much more successful in detecting both of the errors in the query. Okay, so we've generated data for the sake of explaining queries. And now I want to focus on the data generation component itself and show you how to generate synthetic links between database tables for the sake of generating complex relational databases. And this work was published in SIGMOD of 2021. So synthetic data generation has multiple motivations, but again, let me focus on a specific use case. Once every few years, the US Census Bureau collects data about the US population. And they are very thorough about it. For us specifically, they called us 6 times where we had to tell them, stop harassing us. But after collecting the data, the census needs to publish some of it for other agencies and organizations to analyze and draw conclusions from. So in this case, it's crucial to maintain data privacy while preserving the necessary data characteristics and statistics that the census releases to other people and organizations. So one approach which is actually used by census today is to use differentially private mechanisms to release noisy statistics and summaries. However, this approach has 2 main drawbacks. The first one is that we can have inconsistencies. We can ask what is the number of people in Chicago and get 9 million. And then ask what is the number of people in Chicago over the age of 30 and get 9.2 million. The second drawback is that it's—
These are real examples?
This specifically not a real example, but there are plenty of examples where it happens.
That's it. That's fair to differential privacy. The
Yeah.
noise in the query between should be more or less proportional to a single person. So you shouldn't get 200,000 more.
Right. It may be overestimating the error, but yes, but it can have such inconsistencies. And the second drawback is that it's difficult to provide explanation because we only have access to these noisy statistics and we can only get these noisy aggregates and we don't have access to the data itself. So a practical solution in this case can be to generate synthetic data that mimics the properties of the original data. So consider these 2 census tables. that were individually generated using automatic systems. The first one is a persons table containing for each person their age, their relationship to their homeowner, and whether they're multilingual. The second table is a housing table containing for each household, denoted here by a number, the area in which it is located. So as I've mentioned, these two individual tables can be generated using a wealth of prior work. But now let's imagine that this HID column that we have in the housing table also exists in the persons table. So if that were the case, this column would have been called the foreign key. And we could do two things. We could tell for each person the household that they're in, and we could perform the very common operation in databases called joins. So joins allow us to reason and query about complex relationships in the database. So if we were to join the two tables, given this column, we would get a new table called the join view that connects each person with the area in which their household is located. So I've added this column, but now it's empty, it doesn't have any values. And the question is, how do we assign values to it? So one approach is to look at the HID column in the housing table, look at the available values, and just arbitrarily assign each person with a value. However, this can result in problematic data. For example, here we have 6 homeowners in the same household and no homeowners in the New York City area. So to make sure that we create realistic data, we can consider 2 types of constraints. The first one is a type of integrity constraints called denial constraints. And these can be applied on the persons table. For example, no 2 homeowners can reside in the same home. The second type are statistical or cardinality constraints that can be applied on the join. For example, the number of homeowners in Chicago must be 4. By the way, these constraints are available to researchers on the web. Yeah.
אני עדיין לא מבין איך זה מייצר סטטיסטיקות שהן נכונות, אם אתה מרשה לשאול מה שאתה רוצה כי מהג'וין אפשר גם לשאול מה הגיל הממוצע בשיקגו, מה הגיל הממוצע בניו יורק, ויכול להיות שזה יהיה נכון אם כל הזקנים הם בניו יורק, ויכול להיות שזה לא נכון. גם אם אתה, נגיד, בוחר את הסוגים האלה של הסטרנס הספציפיים האלה.
נכון. אז הרעיון בייצור סינתטי, דאטה סינתטי זה עדיין לשמור על הפרטיות, עדיין יכול להיות שיהיה discrepancies בין ה-private data ל-synthetic data, וזה בדיוק מה שאנחנו רוצים, אנחנו לא רוצים לחשוף את הדאטה.
מה זה פרטיות? כשאתה אומר פרטיות אני מתבלבל, תגדיר לי פרטיות. זה הגדרה מתמטית, בלי מילים.
אוקיי.
כאילו זה הגדרה.
כן, אז מבחינת פרטיות אנחנו מדברים על ההגדרה של differential privacy.
אז זה מה שזרקת, מה שטרשת בפור, בסדר?
כן.
ומבחינת הקואליטי, על מה אתה מבטיח?
מבחינת הקואליטי, אז אנחנו נדבר בניסויים על ה-errors, אבל מה שהפתרון מבטיח זה שאנחנו נספק את ה-denial constraint, שהם הכי חשובים לנו מבחינת האינטגריטי של הדאטה.
אז לא הבנתי, אז לא הבנתי את התשובה לשאלה שלי, סליחה, אולי אישה הייתה, אני חושב שלך הוא ענה, לא?
הוא ענה לי שהפרייבסי זה differential privacy, ובקואליטי אתה לא מבטיח כלום. זה מה שאני הבנתי.
בקואליטי אני מבטיח שאני אספק את ה-denial constraint.
כן, אז התשובה לשאלה שלי זה שנגיד אתה עלול להסיק מהאסיינמנט של ה-foreign key שאוכלוסייה בשיקגו זקנה יותר, וזה יכול להיות נכון או לא נכון, יכול להיות שהיא דווקא צעירה יותר, ואת זה אתה לא דורש. כלומר, זה אני חושב ששי מתכוון, שאין שום אינטגריטי, אתה מרשה עוד שאילתות במבנה של הדאטאבייס, אבל אתה לא שולט על הנכונות שלהם.
אז מבחינת ה-synthetic data generation, אז אנחנו יכולים, הרעיון הוא להשתמש במערכות אחרות, כדי לייצר את הטבלאות האינדיבידואליות. המערכות האחרות האלה, בדרך כלל אין להם גרנטיז מאוד מאוד פורמליים, אבל לפחות מה שאנחנו מקבלים זה פתרון ל-inconsistencies וליכולת לספק הסברים, כי עכשיו יש לנו דאטה שעל גביו אנחנו יכולים לעשות שאילתות, הוא יכול להיות נאמן למקור או פחות נאמן למקור, אבל לפחות יש לנו את הדאטה. כן, אז כאילו הייתי אומר, הדראבק אולי זה שאנחנו לא משתמשים יותר בדאטה המקורי. אוקיי. More question? Yeah.
I don't understand the question, the problem. So you have two disjoint tables.
Yes.
You want to join them in order to answer queries?
In order to answer.
Join them in a way that satisfies certain constraints, and you want to answer the queries in a private manner.
No, so once okay, once these tables have been generated by previous work, the tables have been generated by previous work. This can be done. The individual tables can be generated from the private data.
So this is after applying the differential privacy mechanism?
Yeah, the systems that produce these tables do preserve differential privacy.
So you have two different differential privacy mechanisms, one for the right table, one for the left.
Yes.
Now you want to join them.
Yes, exactly.
Why
And this
can't
is the
the
problem.
same systems produce a joint table or?
Why can they account for the foreign keys themselves?
It's like formally, it seems formally the same problem, right? Because they also have to account for like higher level statistics and all that. I mean, the problems that you mentioned now also happen at the individual table level.
In the individual table level, they can't account for, they can generate the joint view alone, potentially, but to account for the denial constraints in the individual table, they can't. So you can let them, you can allow them to generate the joint view, but then to go back to the original table, that's fine. Because you don't necessarily know that how to go back. It's not necessarily one-to-one.
Yeah. When you generate tables that satisfy certain differential privacy constraints, usually generate them with respect to a certain set of queries. Now, after you do the joins, I mean, the set of queries may change, and therefore your table may not be differentially private anymore.
Yeah. So the systems. I don't know about. I have to say that I'm not familiar with. I'm familiar with systems that generate synthetic data based on workloads of queries, and these are not differentially private. The systems that I know, the systems that do generate synthetic data in a differentially private manner, they do it usually by constraints for individual tables, so statistics and integrity constraints. So they're not necessarily query oriented.
I mean, they have to be private against something. Right?
Yeah,
so what is this something? You generate a table to be able to protect from something.
Right.
When you join two things, this something may be lost. So.
I mean, it's post-processing. We have two different things.
Yeah.
Getting what I'm
Yeah.
saying. Suppose you have a databases of males and a databases of females, and sorry for being not politically correct. Suppose you want to join males and females to couples. Then if you do it randomly, you get random couples.
Yeah, but this is
almost private.
Right? Yeah, I mean, if you do something about it, no, zero information is private, of course.
Yeah.
I think this is
So to generate the joins, we're not relying on the private data at all. We're just looking at the tables themselves, and they synthetically generated
something different.
No, it's only the constraint that it's like I did the constraint that each couple is one male and one female, so it will be not correct. And this was the constraint, and you can do it with the data set of male and female.
There's any information.
What?
It doesn't mean that it carry any information.
I agree, except the couple is only male and female.
No.
Yeah. So we're not using the private data to generate these joins. Okay. So now, after defining these constraints, the problem is to complete the HID calling here while satisfying both types of constraints. So first, we know that the decision version of the problem is NP-hard data complexity, and this can be shown using a reduction from null equal to reset. So since the problem is hard, our solution relies on heuristics and can be divided into two phases. In the first phase, we complete the join view while satisfying the cardinality constraints. And in the second phase, we complete the foreign keys themselves while ensuring that we satisfy the denial constraints. So the first phase, completing the join view, relies on a characterization of the relationship between the cardinality constraints, or CC. CCs can be disjoint, contained in one another, or intersect. So for example, CC1 and CC2 are disjoint, since no tuple that contributes to the count of CC1 can contribute to the count of CC2, and vice versa. On the other hand, CC4 is contained in CC3, since every tuple that contributes to the count of CC4 also contributes to the count of CC3. And we say the two CCs intersect if they're not disjoint, nor one is contained in the other. So the algorithm for completing the join view is as follows. We generate a forest of lattices that models the containment relationship, as we see an example on the slide. And then we remove all the lattices that contain intersecting CCs. We then traverse the remaining lattices in a bottom-up fashion, satisfying the CCs while completing the appropriate tuples in the join view. And for the remaining CCs, we model the problem of completing them using the remaining tuples or rows in the table, but as an integer linear program, and we further augment this program with additional cardinality constraints called marginals, which we know from the existing attributes that we have in the join. So now that we've completed the join view, we want to complete the foreign keys themselves, and in this phase, we reduce the problem to graph coloring. So we first generate a conflict graph based on the rows in the persons table in our example. In the conflict graph, we have a node for each row in the table, and we have an edge for every set of rows, such that if this set of rows gets the same HID value, they would violate a denial constraint. So in our example, if we have the denial constraint, no two homeowners can reside in the same home, and we have the first two rows whose relationship is owner, then there's an edge between them in the conflict graph, the red edge. So then we show that a proper coloring of this graph implies an assignment to the persons table, to the HID value, to the HID column, that satisfies all denial constraints. But now recall that we've actually completed the join view. So we have a list of candidates for each person. For example, in our example, if I know that Barack Obama lives in the Chicago area, then I can look at the housing table and only consider the households located in the Chicago area. And these are the candidates for Barack Obama. So actually, the problem of coloring the graph is a version of graph coloring called list coloring, where every node has a predetermined list of colors that it can take. So since this problem is still hard, in practice, we color the graph in a greedy manner.
איך אתם מייצאים את הגרף? יש 50 מיליון homeowners בארצות הברית,
Very good question.
50 מיליון בריבוע.
Very good question. We can split the graph, partition it into connected components. Each connected component are only the tuples with the same area value in our example. So this worked in practice. Yeah, we would get huge graphs for large databases, but then we split them into connected components, and this became the problem. This made
עדיין זה לא 50 מיליון בריבוע, זה מיליון בריבוע, נגיד לשיקגו או לניו יורק.
Yeah, so we've also used good servers with but this optimization worked well in practice. Because the connected components. Okay, I can give you a more specific case where we had.
How large are your graphs then?
I can check and get back to you. I don't remember the exact numbers. Yeah, but they were pretty big, and then we partitioned them into connected components. Now the connected components, in this case, we only have one attribute for the example, but if we have more attributes, then the specific combinations become more rare. Then the connected components in practice are smaller. Yeah.
So this algorithm does not relate to differential privacy, right?
No.
So where is differential privacy gets into this picture? You mentioned it at the beginning, right? I got lost.
Yeah. So differential privacy is used to generate the individual tables that just to make sure that we preserve the privacy of the data, but to generate the joins themselves, the foreign keys themselves, we don't need to look at the specific data. We just consider the individual tables and the two types of constraints. So we don't need to even look at the private data in Chord. Yeah. Okay, so the algorithm that I was describing preserves the property that it will satisfy all the null constraints, but since we solved this graph coloring problem in a greedy approach, we may have to add tuples to the second table, the housing table in our example, and this may introduce some error to the cardinality constraints. So as part of our accuracy experiments, we've compared our approach to two different baseline versions. The first one completes the join view using only the ILP approach without the lattice algorithm, and then assigns foreign keys arbitrarily based on the list of candidates for each row. The second version of the baseline is identical to the first one, but it just augments the ILP with marginals, as does our solution. So here are the results for non-intersecting cardinality constraints, and this is averaged over different scales of the census data. So the first version of the baseline had errors for both types of constraints. The second version had errors for the denal constraints, and our version was able to satisfy both types of constraints. So I think I'm going to skip our ongoing work just to leave time for more questions. Okay. So the general takeaway from my previous research and my ongoing research is that we can provide users with tools that assist them in the data science process, and specifically in understanding and verifying its intermediate results. But often for the tool to be effective, we have to customize it based on the setting of the system, the background of the user, of course, and the requirements from the tool.
Okay.
There are several interesting directions to go into next on the subject of informed data science. For example, providing causal insights for different components, such as the data repair component.
זה משהו קטן? אוקיי.
הוא יכול, זה הוא. אולי זה הרוב.
Okay, so we were talking about causal insights for different components. So to give an example, we can look at the data repair component, and given a repair of interest to the user, try to assign responsibility for different integrity constraints that contributed to the repair, and also assign responsibility to different parts of the data that were combined with these constraints for this specific repair, and also account for implicit effects if we have a causal model available. We can also look at explanations and insights for other components, such as the machine learning model and automated feature engineering. So today, there are several components along the pipeline that can use differential privacy, such as the machine learning training and, of course, the automated data generation, as we've seen. So this adds a further layer of complexity to these already complex systems, so their results are even harder to understand. So what we can try to do, at least for the data generation component, is to provide users with the queries or the classes of queries and the type of tasks that the synthetic data can reliably be used for with respect to the private data. We can also consider explanations and insights as the basis for repair suggestions. So going back to the example of data repair, if we have integrity constraints that are used to repair the data and the user notices a wrong repair, we can assign responsibility. If we can assign responsibility to the culprit constraints, we can possibly suggest refining them so the repair of interest that is wrong would not occur, and then also check the global effect of refining these constraints on repairing the rest of the data. So to conclude, my general research vision is to close the gap between the complex systems along the pipeline and the ability to use them in an informed manner, that is, to be able to understand them and verify their results. Thank you. Yeah.
Another general question. At the beginning, you talked about machine learning and how to use machine learning, but somehow in everything that sort of I understood, you are sort of looking at the data very carefully and maybe giving answers on the past. But sort of there is a mismatch, sort of, if you want to ask queries about the future, how do you choose?
What do you mean queries about the future?
Machine learning is about the future, right? So I want to ask, here is a set of students, how many of them will finish, will graduate, right?
Mm-hmm. Yeah.
It's not a query about the past, but it's a query about the future.
Yeah, so the goal is to try to explain and being able to verify and assist all of the components, in all of the components. So the component can be the machine learning model, but it can also be steps that precede it from, for example, the data repair, the data labeling that can also be done using automatic systems.
I'm lost, but how do you do it in your framework? Okay, so I have a Tel Aviv University database of previous students, and I have the new class that entered this year, and I want to ask how many of them will graduate. How will this?
So you're asking.
Approach.
So you're okay. So you're
like
asking
a different approach to answer this question. I'm sort of not clear how.
So I'm not trying to answer this question. This is what I think what you're talking about is explanations for the machine learning model itself, right?
In alternative to the machine learning, right? So you want something about the future.
Yeah. So I'm what I'm currently focused on. I'm also working on explanations for machine learning. I think that's what you were aiming for, but I'm not sure. I'll be happy to discuss, but what I'm saying is that the data science process is composed of steps that precede the machine learning model, even to prepare the data for the machine learning model. So these steps can be problematic as well, and it's not clear how to verify the results. Yeah.
So a very concrete question, something that I missed during the talk. So in the operation that you mentioned just 10 minutes ago, so you said each individual table has differential privacy.
Yeah.
The one thing I didn't understand is whether the operation preserves differential privacy.
Assigning the join values.
So you take two differentially private tables.
Yeah. When
you do the join, does differential privacy is it preserved?
Preserved no matter what you do.
Yeah, because I'm not looking at the data itself.
Wait, I want to hear.
Yeah, I'm doing it as a post-processing step. Yeah, so what I'm doing is I've generated using a differentially private mechanism or several. I've generated synthetic data somehow using, I don't know, some kind of magic, and then whatever I do with the data, without looking at the private data, will not violate differential privacy because I'm not even looking at the private data.
So it's like the random.
Yeah, it's a post-processing step.
Okay.
Yeah, just to allow me to create more complex data and not just individual tables that are disconnected from one another.
May lose accuracy and.
Yes.
Okay.
Yes.
Understand.
hopefully not, but yes. Yes.
In the coloring algorithm that you described, we don't know how to approximate graph coloring, right?
It doesn't approximate it, it's just a greedy approach.
Even if the graph can be colored with 3 colors, we don't know how to color it less than n to the 0.1 color. So,
Yes.
I mean, how useful is this?
Oh, how useful is this? So as a standalone algorithm for the problem of list coloring, I'm not sure how useful it is.
No, how useful is such a bad result?
Oh, so in practice, what we're doing does guarantee the satisfaction of all denial constraints because we're allowing to, in the analogy of graph coloring, we're allowing to expand the list.
No, but I mean, instead of having 3 colors, you have n colors. I mean, you can color everything with n colors.
Yes.
So why not do that?
So we can do that, but our goal is to try to do that with as close to the list of colors as possible. So we're dynamically expanding the list if we have to, but if we don't have to, then.
No, I understand, but we know that theoretically you may need to expand it by a lot.
לא, אבל מה עוזר המספר הקטן של הצבעים בסוף? אם זה לא, מה שאמיר אומר, אם זה לא חשוב לך כמה צבעים יש, אז אל תתאמץ. אבל אם זה חשוב, צריך להתאמץ.
כן, אז זה כן חשוב לי, ואנחנו כן מתאמצים, אנחנו עושים את זה פשוט בצורה דינמית.
לא, אבל השאלה, מה היה, למה התשובה שאתה תיתן תהיה לא טובה אם יהיה אין צבעים?
אם יהיה המון צבעים, נניח שיש המון צבעים, אתה לא עושה אופטימיזציה על מספר הצבעים, מה זה חשוב? או לפחות האם יש איזשהו גרנטי בגלל הסוג של הדאטה שלך שאתה כן יכול להגיד.
אז הגרנטי הוא שאני אספק את ה-denial constraints, את האילוצים בכחול, ואני רוצה כן לנסות לצבוע אותם עם הרשימות הנתונות שלי לכל צומת, אבל ברור שאני ברוב הפעמים לא אוכל, ובגלל זה אני הרבה פעמים צריך להרחיב אותם, אבל ההרחבה הזאת לא תהיה על חשבון ה-denial constraints. ה-denial constraints... אבל
היא תהיה על חשבון מה?
היא תהיה על חשבון ה-cardinality constraints, ואני אולי אוסיף טאפלים מלאכותיים, שורות מלאכותיות, לטבלה השנייה.
אבל עדיין הדאטה meaningful, אם אתה צריך להשתמש בשור של צבעים במקום בשבע?
לא, לא. אז הסטטיסטיקה מתרחקת ממספר ההורמונים הזה שקיים.
כן, אז העניין הוא כזה, אם האילוצים שלי הם לא אינטרסקטינג, אוקיי, העניין הוא, כן, זה ניואנס, אוקיי, זה ניואנס מעניין, אם האילוצים שלי הם נון אינטרסקטינג, אז אני יכול להראות שאני אספק את שניהם, אני אספק את ה...
זה סוג של גרף שאותו אתה יכול לצבוע ביעילות?
לא בהכרח, לא בהכרח, אין לי גרנטיז על הצביעה של הגרף.
לא, אבל אז אם אתה מקבל המון צבעים, אז זה הורס לחלוטין את כל הניתוח שאתה עושה? מה זה עושה?
אם אני חייב להוסיף המון צבעים, אז כן, אני אקבל דאטה שהוא לא בהכרח טוב.
ואתה יודע להגיד שהדאטה שאתה מקבל הוא לא כזה?
אני יכול למדוד את השגיאה לעומת הקונסטריינטס שלי, ואז להגיד, טוב, אני שגיתי, כאילו, הארור בקונסטריינטס הוא ענק, אז אולי עדיף שלא להשתמש בזה.
כן, אתה רואה. כלומר, יש לו נגיד cardinality constraints,
בהם
הוא מוותר, ואתה יכול לראות אם ויתרת הרבה או ויתרת מעט.
יש כאן שעניין לדעת בסוף לדעת בהתחלה.
כן, יש לי פשוט, אוקיי, אם אני יכול מראש, לפני שאני...
כאילו אם אתה בוורסט קייס.
אבל זה מה שהגיוני, זה להגיד בוא ננסה לצבוע במעט צבעים, אם הצלחנו ולא סטינו בהרבה מהקונסטריינטס, אז אתה יודע מה יש לך חסם על מה שקיבלת.
זה לוקח זמן.
כן, נכון.
אנשים צובעים גרפים.
אני לא מכיר כאלה.
אתה לא מפחיד אותה מספיק בסימוכיות, הם מנסים בכל זאת.
עכשיו אתה מכיר.
אוקיי, תודה רבה.
אני הולך לארוחת צהריים, אני פה